So just first off, is there any problems with the labs now? Anyone that doesn't have access or have any other issue? Because yeah, the deadline for the lab 1 is tomorrow, and also lab 2 will be I think the 1st of February. So if you have any problems to get access, please sort this now or as soon as possible. Yeah. Right. So today we will finish off with chapter 2, which is kind of the chapter which talks about all the basic abstractions in the book or in distributed systems. So remember, last time we left off with a brief introduction to failure detectors, and hopefully today I will go through them more in details because they are very central to distributed systems because they act as a sort of a link between, or let's say a common abstraction between processes and links. So yeah, we okay, Raymond, just if you can write this message on the Discord, I will check this afterwards. Yeah, so we briefly saw this ping pong type of failure detector, and we also saw the heartbeat example, which is similar to the one that you will implement in the labs. And then we looked into the perfect failure detector. I think we only discussed it very briefly, but I can do this again today. So the important thing to note in the perfect failure detector is that this works only in the synchronous time model. So you need to be clear about this when you analyze the algorithm, so that you will know the underlying properties of the system. But this has two properties: strong completeness. Every process that is crashed is permanently detected by every correct process. So this means that once a process is crashed, it will never recover again. It's considered crashed forever. And as you see, it says eventually, meaning that here this doesn't necessarily happen at the same time in the entire network. The processes might be detected crashed at different times by different processes. And then we have the strong accuracy property. So here it says that if a process is detected crashed by any process, then the process P has crashed. So here again we have something that will not, it's very obvious later on that you will see that such a property is not something that you can trivially you have in an asynchronous time model. But since we are in the synchronous model, then you can have such a property. So the algorithm itself, I wanted to go through this because this is very similar to the one that you will do in the lab. Only that in the lab, obviously, it will not be the synchronous time model. So the first thing that you should notice when you analyze such an algorithm is the uses part. So here we see that this uses perfect P2P links. So this means basically that it's another abstraction on top of the links that we saw, link abstraction we saw last time. And by the way, such algorithms as this, that you will most likely be asked to either analyze such an algorithm on the exam or write one yourself for different protocols. So it's useful to get used to this. But yeah, so we see here that we have 4 events. We have the init event, which basically sets up everything, and it starts at timer delta. And then we have a timeout event. Oh, by the way, I can see if I can have my mouse there. So the timeout event, this timeout event basically triggers whenever this timer finishes. So this algorithm, it doesn't say how long is the timer, but you can infer from this that the timer will be set to some delay, and whenever this timer finishes or stops, the timeout event will trigger, and then the algorithm will do some action. So what it does there is that it checks all the processes in the capital P symbol, meaning that this is the set of alive processes. So initially, all processes are considered to be alive. So the next condition here checks that if P is not alive and P is not detected in the detected set, then we will first set it to detected and trigger a crash event up the stack. So then we will send continue sending heartbeat request to the processes. So the second part of the algorithm basically is like the ping pong thing, that whenever you get a heartbeat request, you send the heartbeat reply back. And if you get the heartbeat reply back, then you can also assume that this process is alive, and you will add it back to the alive set. So like one thing that you can notice in this algorithm is, for example, that it keeps sending heartbeats to processes that it has detected crashed. So this type of optimization is very obvious when you are in your actual code, that you will not continue trying to send to a process that you have already said is crashed. It doesn't make sense. But oftentimes in these pseudocode algorithms, they have abstracted these details away from us. So next, I thought that we could try similarly to last time, because last time we draw this module composition for a perfect P2P link. But do you remember at all how you would do this for a perfect failure detector from what you saw already? Because this is some easy points for your exam, that if you can answer this question, then already you have gotten some points. So I will not spend too much time on this, but I just wanted to make it obvious to you that this is something you need to practice. So what we will do is that we can just copy the thing that we had last time and start from there. So I think we were on this slide. Yeah. So so we saw in the module, no, I mean in the algorithm description, that it uses perfect P2P links, and since we already know what happens further down the stack from P2P links, it's not necessary for us to do this work again. But the only difference now is that we will need to move our application and then have another layer between the application and the P2P links. So I'll try to make this arrows very small. The main thing is that you will get the point. But yeah, so in this module it will be the, what was it called, perfect failure detector. And let's see, maybe two large text. Yeah, and then we still have, basically always you will have an application on top, which yeah, it's like a good point to start with, that you will have an application. And then now the only thing that we is missing here is that how does the application communicate with the perfect failure detector? So you notice in the links abstractions there that everyone had like a send, deliver, send, deliver, send, deliver, but obviously it doesn't make so much sense that the application will send something to the failure detector. I cannot imagine like what will it send. So clearly it should be something different, but when we inspect the module description here, it says that there's only one indication event. So there's one indication event here. So it's a little bit different from the ones we saw previously, because it has this pipe symbol or the bar symbol, and then the argument P here. So this indication event, it comes from the perfect failure detector with the name crash, and then it carries the parameter P, which is the processes that was crashed or had crashed. So where did I put this here? So the only thing that we need to add to complete our drawing here is that we need just one event that goes up to the application, which should have this name that we saw. So it should be P, and then the name of the event, crash, and then also if you add the parameter or argument, this is a very respectable answer on the exam. So yeah, now you know how to answer such a question, and you know, it's not only in this part with failure detectors, it will also be in the broadcast algorithms and in the consensus algorithms that it will be necessary to think about this, the underlying abstractions that every algorithm uses. Right. So yeah, as I said, this perfect failure detector, this is in the synchronous model, and as you also know from last time, the synchronous model is not something that we can assume very often. Most of the time it will be the eventually synchronous or the partial synchronous. So if you have this perfect failure detector assumption and you still decide to use it, there is always considerations that you need to do between this timeout and setting this timeout to the correct level is not something that's so trivial to do. So if you set the timeout to be very short, your algorithm will work fast. It will detect any failures very quickly, but there's also the probability that you will have a false detection because maybe the other processes are working slowly and they didn't get time to respond, but you will, due to that you have a short timeout, you will trigger them as faulty anyway. And on the opposite side, if you have a very long timeout, then you will detect any failures late, but you will have a much lower probability for false detection. So it's typically impossible to set the timeout to be perfect. And you will also see this in the next algorithms there. And then, yeah, the failure detectors, this is used to detect a failure in your system or a process that has failed. But often you're more interested in finding a process that has not failed, or one process that you know is correct. And this is very typically used in many distributed algorithms, such as consensus algorithms. And the typical example is with the primary backup replication scheme. I'm sure you are somewhat familiar with this, but basically what this very simple system here does is that you have 3 replicas. Here they are just named leader, follower 1, and follower 2, but you can imagine that these 3 processes here, they are storing your data. Let's say you have you have backed up your data to 3 hard drives there. So when you either want to store some more data or you want to retrieve, but let's say in this case that you want to upload a new photo, for example, to your disk system here. The client sends the request to the lead. Usually he will send to the leader, but this is not strictly necessary always. But let's say that he sends the request to the leader does some processing. Then an important step here is that the leader sends a message to the 2 other replicas that they must also update their local storage, meaning that even if the leader is storing this new photo that you requested, the leader needs to make sure that the other replicas are also storing this. And only when the other replicas confirm back that they are also storing this photo, then the leader will send back a message to the client that now everything is fine. So this is like the sequence flow of this algorithm. So this is very typical in our course, that like the sequence flow or time flow of algorithms will be described in this way. So again, if something is not clear, please just ask. So yeah, the arrows here, they are sort of denoting time, meaning that the time it grows on the horizontal axis here. Yeah. So in the event that the leader crashes, he needs to the algorithm needs to decide a new leader. So in this case, we have that your client sent a request to the leader to store his photo. And in this case, the leader he wrote the photo, the data to his hard drive, and after he sent a message to the 2 different replicas that you need to also update your local storage. But when these 2 replicas tried to send the acknowledgement back, the leader was crashed. So this means that the client will never receive a response back from the leader because he is crashed. So after some time, the client will send a new request, and in this case, we have that since the old leader was crashed, follower 1 is elected to the new leader in this ellipsis symbol here. During this phase here, these 2 processes that are left, they did agree on that follower 1 should be the new leader. And yeah, thus when the client sends the new request, he gets the result back. So now we will have a very similar example, and you need to always, when you have these flows, you need to read very carefully when does this crash happen. So previously, in the example we discussed, the leader got the message, he did the processing, he sent the update to the other replicas, and only after the leader has sent the update, he crashed. But it's also possible that he does the processing, and then he crashes before he was able to send the update to the different replicas. So in this case, the agreement between the two followers will happen again, but when the client sends the request, these two need to, or when the oh, yeah, you can see here that in this case the client sends the request to the follower 2, but actually it was the follower 1 that was selected as the leader, and thus the follower 2 relays the request back to the current leader. Afterwards, the leader does the processing as the old leader would have done. And very importantly here that this processing step, it needs to have the exact same result as the old leader. So this is something you need to be clear about. And afterwards, the protocol happens as before. He sends the acknowledgement message back. And yeah, in this case, he asked the follower 2 to relay back the request to client 1. So this is what is typically called the primary backup protocol, that you have a primary, and whenever the primary fails, there's a backup to take his place. So we will see much more of this or similar to this in consensus protocols. Yeah. So now, yeah, I guess I skipped the module description of the leader detector, but yeah, so this is a leader detector. The module description, that's one indication event, so no request events, just indication event that replies back that whoever process it considers as the leader. So yeah, it has eventually detection property. Either there is no correct process, I mean that if there's no correct process in the system, or one correct process is eventually elected as the leader. So it basically means that if there is one correct process, there will be a leader eventually. Yeah, and the accuracy property here states that if a process is a leader, then all previously elected leaders have crashed. So from this one, you can clearly see that this is only considering the crash stop abstraction. So because if it was a crash recovery, we could not, or we cannot have these two properties at the same time. Because a crashed in a crash recovery, it would be a correct process. Yeah, so this is one module description, and then the algorithm for this is here. It's very short because it's basically using the perfect failure detector that we saw previously. So it just sets up like a suspected set that it received from the underlying failure detector, and a leader with this strange normal symbol. So this init event basically means that when it starts up, it has no leader. There is no leader chosen yet. And then the event to do the choosing of the leader, it's down here saying that so whenever the leader is not equal to the maximum rank of the capital P / suspected, do this thing. So if we break down this if condition here, or event condition, so leader, this is obviously your local variable that you have here. This symbol means not equal. And then the max rank function, this is like, you can imagine that you have an array of numbers, let's say, and or process identificators, and then you evaluate each one in your process set to find whoever you rank the highest. So typically that you can do this to, for example, have the IP of the process and use this as the rank, or you can have some predefined setup that you say that, oh, the process with this address, it has rank 3, and then a different one has a rank 4, and so on. Because remember, in the algorithms that we will consider here, we always know beforehand our processes and how many processes will be in the system. And the backward slash here, it just means that you are removing the process that are suspected. So the next line, it basically, you take the rank that you found and you put this to the variable. So again, you see that it's very clear that there's a optimization that is not considered here. For example, if we in a normal programming language, you would just store the result of this max rank function, because if you have thousands of processes, it can be very expensive if you need to check every single one. So it doesn't make sense to check this on your if event here, and then you have to do the evaluation again straightly afterwards. But typically, this sort of optimizations is left out of pseudocode. So whenever you're asked to do the same thing, to write a pseudocode for an algorithm, you don't need to worry about such optimizations. It's more important that it's clear to read and it's correct. Yeah, and finally it triggers the leader event up through the stack. Yes, let's see what's next. Yeah, so the next thing is that we are in the partially synchronous model. And remember, in the partially synchronous model, we are most of the time in a synchronous period, but sometimes the system will behave asynchronously. So this is why typically any algorithms that is designed to work in the partially synchronous model, they have this keyword eventually. And there is even a special sign, this square here, or diamond symbol here, in distributed systems and in what we call temporal logic. This symbol means eventually. So when you see this symbol, you have to know that this means eventually, because sometimes this is just left out, that people in the distributed systems community, they assume that everyone knows what this diamond means. So just try to note this down, that this diamond here, it means eventually. So this this indication events here, it basically says for the eventually perfect failure detector. So remember this P here, it has the it was the abbreviation for the just the perfect failure detector in the synchronous model, and then they add the diamond beforehand, so the full name would be eventually perfect failure detector. So yeah, this module here, it has two events: a suspect event and then a restore event. That this model, it allows to that you suspect someone, but afterwards you go back on your suspicion and say that I'm not really suspecting him any longer. Yes. So this is actually very similar to the failure detectors in lab 3. So try to follow along with the algorithm, and it will be more easier for you in the labs. Yes. So last thing I want to say is that these properties here, that they are very similar to the ones that we had for the perfect failure detector. In the perfect failure detector, we had also a strong completeness property, but and then we have the strong accuracy in the perfect failure detector model, but here we have the eventual strong accuracy, that we have a similar thing, only with the eventually keyword, meaning that eventually that the system will have a clear state on who is failed. So this algorithm here, again, similar to the ones we saw for the perfect failure detector, but remember that now we are in the partially synchronous model, and thus we do not know what is the appropriate timeout to set. We just know that there is an upper bound, but this upper bound is unknown to us. So yeah, you can see how this is solved with the name here. It's solved with an increasing timeout, and initially you initialize the variables the same way, only that now you have a delay variable here set to some delta, and again you start the timer initially with this delta. So whenever you have a suspicion and then you're increasing your delay variable. So yeah, this first condition here says if the alive set intersects with the suspected set is not 0. So this means that one of the processes that you considered alive is now also in the suspected set. So you do the intersection between these two sets, and if it's non-empty, then you increase your timeout. And then you have a for loop to check all the processes in your system. If the process is not alive and it's not suspected, then add it to the suspected set and send out suspect event up the stack. So you you get the you don't consider this process to be alive, and you don't consider it to be suspected. And only in this case you will add it to the suspected set. And if it's you consider it to be alive and suspected, then you remove it from your suspected set, because if it's both alive and suspected, then it should only be alive. Yeah, and then afterwards you clear your alive set and you start the timer again. So we can imagine that whenever you get a response back on the end here, you get a heartbeat reply from someone, then you're adding this to the alive set. So yeah. So this first part here is basically saying in the cases that you you get the it's kind of that you get the alive message or heartbeat reply, and you add the process to your alive set after a timeout has been run. So a timeout event has been run, and before this time you didn't receive this heartbeat reply, and thus you had this if condition happen, that you added this process to the suspected set, and then you sent up the suspected event through the stack. Only on the next iterations of the timeout, then you have it so that now actually this process is in both the alive and suspected set. And from this, you deduce that a process cannot be both alive and suspected, thus that your unknown timeout that you started with initially, it needs to be increased. So you are trying to increase your timeout to have a better accuracy on whoever's failed. So if we started this algorithm with a very, very small delay, like for example 0.1 millisecond, then it would send a lot of suspect events until this timeout was reached a level where it matches the communication delay between the process itself. So that's that. Yeah, this algorithm, it will be on lab 3, and I think on lab 3 you can do the options to have the increase to be a constant here, or you can also increase it with some factor that, you know, to double the delay, for example. Yeah, you will see what's the best solution. And one problem with this is that if you have one process that is acting very slowly during some time, then you'll keep increasing the delay. But if this period of asynchrony stops in that process, that it goes back to being synchronous, this algorithm, it will never reset the delay, so it will always keep the delay at a very, very high level. So to improve on this algorithm, you will need to reduce the delay somehow. And then we have the eventual leader election, and don't worry about sometimes this book actually says there's a leader election and sometimes a leader detector. So I think this is a ambiguity in the book, so don't worry about that. The main keyword is leader. And again, this is so common that they have its own symbol, this omega or horseshoe symbol. I guess omega is the more appropriate name, but it follows the very similar description from the perfect leader detector, only that now it has the eventual property here. So eventual agreement that there's a time after which two correct process, there's no two correct process trust different correct processes, meaning that eventually, if the system keeps on running for a long time, they will agree on who is considered to be the leader. Yeah, so this algorithm here, it's given in two um, 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 process abstractions, and let's do a 5-minute break before I will continue with this. So I will put up a timer and let's continue in 5 minutes. All right, hello. Is everyone? Okay, 37 seconds to go. Yeah, the questions about the previous presentations. Right now they are only stored in my hard drive here. But I have plans to release them. I just need to check that it's okay to share them with you because that I just copied these algorithm descriptions from the book. So like typically you would only show this in the class or write it on the blackboard, but since we don't have this option, I just copy them into the presentation itself. So I'll have a meeting today with one person that knows about this thing. And also one more thing that I would like your input on is that, well, it's with respect to the exam, and I'm considering to have the home exam where you will sit at home or wherever you want to do the exam. But I never did such an exam myself, so I was just wondering if you have any input on these types of exam, if there is something that is a typically very bad or a fall pit to have on these exams, for example, with the time limit or with the questions themselves, because obviously the question, if it's a home exam, will need to be with all 8 allowed, I guess. So I don't know if anyone have an experience with these types of exams, but well, if you have anything, then you're free to reach out. Otherwise, yeah, we'll probably figure it out. Yeah. Okay. Anyway, so we now we are talking about the eventual leader detector in the partially synchronous time assumption, and as it says here, in the crash stop process abstraction. So in this case, we allow only that a process can crash and it can never come back. So in this case, or almost always in this case, the algorithms will be more simple because you have only 2 states of your process. So this algorithm, it's using the eventually perfect failure detector, as it says here, and basically it's just listening to the 2 events that the failure detector gives it, the suspect event and the restore event, and these 2 events, you see this clearly now that you get the suspect event on a process, you add it to your suspected set, and if you get the restore event, you remove this process from your suspected set. And the leader, it will be whoever has the highest rank, as we discussed previously, that this ranking function, it can be anything as long as it's deterministic. It's up to the implementation itself. So this is the ranking function, and Also in lab 3, you are free to, for the most part, to decide this ranking algorithm yourself. Yeah. So then there is also an eventual leader detector in the crash recovery process abstraction. So you see already this is a bit more involved. The algorithm is much longer, and what you need to always pay attention to is this uses pattern, because if we saw the crash stop is using the eventually perfect failure detector, but in the case that you have a crash recover process abstraction, it's actually using the fair loss point-to-point links. So this is one level underneath the perfect. No, it's actually the lowest level. It's even under the stubborn link. So just to just to be clear, if we go back to the model composition we draw in the start, this this fair, okay, the fair lowest per the fair link is at the very end here. So the fair detector that we saw first was using the layer way up here, but now we are considering an algorithm that's using this very low-level layer. So let's see briefly how this algorithm works. If I can find it here. So here is the first time that you will be introduced to epoch. So epoch, this is also a very key word in distributed systems, and it refers to a time period, and typically in algorithms, we can say that the algorithm moves forward in epochs. That like epoch it's sort of a bigger time period, and inside this epoch many events can happen, but you sort of split up the time in epochs. So but in this algorithm here, the epoch refers only to how many times a process has crashed. So what happens is, well, you have, again, we can just one more thing is that we have the store and retrieve function calls. And remember, this is due to that we are in the crash recover process abstractions. So the store, it means that you take some data and you write it to your stable storage, and retrieve, it means that you are able to retrieve this back. So initially this algorithm, it triggers the recovery event. It finds whoever should be the leader, triggers a trust on this this leader, and gets the epoch that was stored in the database or the stable storage, and increases this. So basically, what these first lines here says that is that the algorithm considers itself to be crashed when, even the first time it starts up, and then it sort of um, adds one to its own epoch. So now ourself will be in epoch 1. And then we will send out a heartbeat with this epoch saying that we have only crashed one time to all the processes. And then we will start the delay timer. And if we jump directly to the deliver event, so that when other processes are sending a heartbeat to us, we will retrieve the heartbeat here. So yeah, I don't know. Yeah, so the first if condition here is kind of long, but what it says is that if there exists an S and E in the set of candidates, so there is a set of candidates to be the leader, and the condition here is that such that S equals Q and E less than epoch. So it's kind of cryptic here, but it tries to capture that we the process Q that has sent the heartbeat, it has a higher epoch than was stored previously. So in this case, we remove it from the set and update. So this is that's what happened. And whenever you have a timeout, you have a function to select candidates, and this is like the max rank function. So yeah, if there is a leader change, you update the delay, and yeah, you set a new leader, you send the trust event, and again on a timeout, you send the heartbeat request and reset the timer. But here the select event, the goal here is to find the candidates that has crashed the least often. But yeah, in this algorithm, the most difficult thing here is maybe this syntax. So yeah, if there's any questions about this, oftentimes it can be written very, very compactly, and it can be difficult to see what it should do. So don't be afraid to ask about such questions. Yeah, and then finally we will see Byzantine leader election, and now we are considering that the processes may behave arbitrarily, meaning that they can deviate anyway from the algorithm, and since they can deviate in any way, then we cannot really rely on time any longer, because they can like the key difficulty here is that they can pretend that they are correct. What is typically done is that you have a trust but verify approach, that um, you you verify all the messages that the different processes send to you, and if you cannot verify, then you will then you will suspect this other processes. So we can see how this works. Now the big difference here is that we no longer have only a leader event, sort of that we had before in the crash stop and crash recover models. We also have a complaint request. So when we are talking about a Byzantine leader detector, then this requires that the application itself send some complaints about the process. So it can typically be that the process that is given to be trusted as the leader, the application itself might not be satisfied that this process is doing its job, and then it will send this complaint event to the rest of the network. So yeah, this these two these three events here, 1 and 3, they sort of replace the accuracy, eventually accurate property that we saw before, and what was the name eventually? Let's see if I have the correct name. Eventually agreement, yeah, on the crash stop abstractions, but it also has the BLD2, the Byzantine leader detector 2 property, putsch resistance. A correct process does not trust a new leader unless at least one correct process has complained against the previous leader. So this property number 2, it captures the times when a Byzantine process tries to tell to everyone that it's the new leader. So even if a Byzantine process tries to like have a takeover, the correct processes will not trust it unless there was some complaints about the previous leader. Yeah. So the algorithm for this is kind of more involved, and we can see here that as typically in the Byzantine algorithms, that it's relying on authenticated perfect links. So usually always in the case where we have a Byzantine algorithm, we need to have a authenticity, typically digital signatures or MACs or cryptographic hashing of the messages. Yeah, so this algorithm, as I said, it has a trust event that's triggered up the stack, and then it can receive a complaint event from the application, and in this case, the complaint, this is like a broadcast that we can see that we get the complaint event on the process P, such that the P, that the process that was complained about, it is the current leader, and we didn't complain yet. So this Boolean variable is set to false. And in this case, we will, for all the process that we know about, we will send the complaint event, and for whatever round we are referring to. So this AL, this is authenticated links, as we see here. And then whenever we get a complaint for our current round, and that we didn't register any complaints about this process yet, we are sort of let's say here we are taking the complaints that we receive, and we are adding this for the process, so that remember that P is, this is the guy who, or the process that sent to us the message, and we are registering his complaints, and whenever we have sufficient complaints, so this hashtag symbol here, it means typically the number of elements in the set. So if there is more elements in the set than F, so F is typically, we will see in the next slides, but whenever you have a Byzantine leader, something with Byzantine, then we have the relationship that the number of nodes in the system must be 3 times F. So yeah, if we have, for example, number of nodes in the system to be 4, then F is 1. So yeah, we will see later on. But this is trying to capture that we have sufficient amount of complaints, and only in this case we will send the complaint, or we will relay the complaint to the different processes. And if this list grows, so that we have an even bigger quorum, then we can continue to the next leader. So if we have so many complaints for this round, bigger than 2F, in this case we will go to the next round, and we will reset our complaints, and we will trigger the trust event for the next leader. Okay, is this algorithm clear for us? Would you be able to draw this in a module composition, for example? You can think about that. Yes, and then the last sub-chapter that we have in the book for this chapter, it's like just a summary of the abstractions, or combining the abstractions from the processes, the links, and the failure detector. So you need to try to be familiar. To draw the module composition, yes, I can. For this one, yeah, we can do this as an exercise. Let's see. If I find the mouse here. Where do you see my mouse? I just saw it. Always something happens. um, Let me. It's not possible to see my mouse on my screen, so I have no idea where I'm pointing now. How can I reset this thing? What the hell? Yeah. Let's see. All right, now I see the mouse. Okay. So are you still seeing the presentation screen? Or not? For some reason, the Zoom application likes to consume 90% of my processor, I think. So I have no idea. All right. Okay, it seems like it's kind of working for me. So let's try to make another slide inside here. Something else. So let's remove this. And okay, we need authenticated perfect point-to-point links. So let's do a little bit cheating here. Let's just copy this to save some time for us. So, okay, authenticated point-to-point links. We need to find this first. So it should be somewhere along the way here. Let's think about this. Maybe here. Oh, first try. Okay, great. So is here this relies on stubborn P2P links. So this means that basically we can use the same model that we had, only that we changed the name to authenticate perfect point-to-point links. Because whenever you see something that uses one higher level abstraction, you can just automatically assume that whatever's underneath this abstraction is the same as every time. It cannot. If this algorithm required something different underneath stubborn point-to-point links, it would not use stubborn point-to-point link. It would use a different abstraction. So yeah, we will just start by changing the name of perfect point-to-point links. So it should just be like out authenticated. Out, for example. Like this. And well, now we are already almost at the goal, because this Byzantine leader of this algorithm, it uses authenticated point-to-point links. The only thing that if we are too fast and we just do it like this, we say that we will just change the name of this Byzantine. First, we have the spelling mistake, but other than that, we have some problems here. So this should be Byzantine. So first we changed the name of this module, but we forgot to change the name of these two events. And yeah, maybe I was too fast because I just changed the name and I didn't really read these two events. So this is something that you need to do. But let's see. I think it was around here. Yeah. So in this case, we are lucky that it has only the send and m events. And if you want to be extra detailed, you can also write these two parameters. But usually, yeah, it's not required, but it's nice to do if you want. So let's update this to AL. So very often students can do something like this and they say, okay, now we are finished with everything. But the problem is that now we actually didn't write anything or do anything about the events of this module, the Byzantine leader, detector, let's say. If you write election or detector, it's the same. Because we need to consider the event that this have. So here we have a trust indication. So indication, this goes up in the stack, and then request, this goes down. So to complete this, we just need to copy the arrows one time and have an application on top. So if we are able to move this, So it's sort of good. So yeah, at the top you can usually write application. Not always, but in this case, we will do it. And then we need to have the events. So it's important that here it must have the name of the module, BLD, Byzantine Leader Detector, and then the name of the event. And if you decide that you want to write them the parameters, also this is also okay. Sometimes it can be necessary if you have many events, for example, that you feel that to properly describe this system, I need to have the complete description. So it will be like this. I mean, here I would BLP, not BLD. But yeah, something like this is so this would be a good answer for the exam. Yeah. Any questions about this this thing? Okay. Yeah, we can also write it here. The main idea here is that to show that you need to show that you know how the system is built, like what's the system composed of, all the modules in the system and how they communicate. Because it's not every time that we will have one nice step like this. It just goes to one down and one arrow up. It can be 2 or 3 arrows up and the one down, and also there can be module in parallel, so that it can be 2 or 3 separate stacks. What's the difference to eventual Byzantine leader election? Difference from what? From this here? So this is actually a eventual leader detector. So in general, you cannot have a perfect Byzantine leader detector because of this thing I wrote here, that when you consider Byzantine faulty process, then it's not possible to rely on time from them. So if we wanted to have a perfect Byzantine failure detector or a leader detector, then we somehow needed to set a specific time to say that, okay, in our system we have a synchrony of 10 seconds, but this is like very easy for a Byzantine process to emulate. So it could just emulate to you that it's responding within 10 seconds, but yeah, actually we need to have a stronger assurance that the process is well behaved or not. So this is why that you'll only find an eventual algorithm for this. Yeah, implements and uses. So, well, what can I say? Implements. This is like talking about uh, this whole algorithm here the complete thing that we see here. This is implementing Byzantine lethal detector, and it means basically that it's implementing an module that we saw previously. If you saw from before that we had, now I've gone back a few slides, but we had the eventual lethal election eventual lethal detector module that we saw, and on this there was two implementations of this. So the algorithm 2.8, it implements this module, and also the algorithm 2.9, it implements this module. So the implements line is just saying what module is this algorithm implementing. But the uses line, or it may be multiple lines, it's saying what other modules am I relying on? For instance, here this monarchical eventual lethal detection, it's relying on the eventually perfect failure detector. So it's saying that it has events from the eventual perfect failure detector that it's relying on. It will not work without this module. But the different implementation of the eventual lethal detector that we saw with using epochs is using a different lower level module. So this is just to show that there is usually many ways to implement a module, and also the implementation will be different on the failure scenarios that you consider. So the key idea here was that in one case we were only considering the crash stop process abstraction, and if we could assume this process abstraction, the implementation was kind of short. There wasn't too much going on, but if we allow processes to also recover after they crash, then we had to have a more involved algorithm. So was it an answer? Yeah. Okay. Just ask again if it would be more simple if we were in a classroom probably. So, but yeah, I'm trying to use my mouse here to point to what I'm talking about. All right, so yeah, we draw this module composition, and yeah, then I was just started with this combined abstractions. So there is 7 of them that is considered in the book. but yeah, not all of them are so relevant for our purposes. Um, but yeah, I will go through them and I will tell you what are the most relevant. So the fail stop, this is the most easy, let's say, simple model that the process just works, and then at one point it can crash and it will never come back. So in this case, in this model, we use the perfect links that we saw, perfect point-to-point links, and we have a perfect fail detector, meaning that now we are talking about a synchronous system here, or time model. So the fail silent. This is a very difficult model that the process can crash, but you don't have any fail detector. So you can never know that someone crashed. So this model will we not have in the labs, for example. Instead, we will have the fail noisy um, abstraction that again crash stop using perfect point-to-point links, but we have a eventually perfect fail detector. So in the fail noisy model, we are in the partially synchronous timing assumption, so that we can assume that if a process crashes, uh, at, after some time, we can eventually detect that there was a failure. Yeah, and then fail recovery. It's similar to the fail noisy, is just that now we uh, also allow the crash process to come back. And yeah, I think in lab 6, the last lab, you will go more into details with this, and why this is not as simple as it sounds. But for lab 3, yeah, and also partially 4 and 5, you will maybe from especially lab 3, you will maybe get the idea that this isn't so difficult, that a process can just come back and there is not any consequences to allowing this recovery. But uh, there is a reason why it needs to be a separate thing here. And yeah, it will be more clear when we go into consensus. And we have a fail silent arbitrary. Again, very difficult thing that now we are talking about a Byzantine process or arbitrary fault process that can deviate anyway from the algorithm. We have perfect authenticated links, meaning that there's a way to authenticate whoever sent the message. But yeah, the messages are authenticated, so they can be you can be sure the process can know who sent it. In this model, you don't have a fail detector. Fail noisy arbitrary, same as before, only that now we have a existence of a fail detector. Yeah, and then the last class or abstraction is just called randomized, and it sort of tries to capture all the cases where your algorithms may not be deterministic, um, and they only have a high probability to solve the problem, and oftentimes this is necessary to have a solution that actually works, and probably um, you're already using such algorithms daily without considering this. But for example, in Bitcoin, they have this thing where um, the hash of the blocks is being pointed by the previous, or the next block is pointing to the previous one, and this part of the algorithm is kind of randomized, because they are, whenever you want to generate a block in the blockchain, you have to input a nonce, and it will generate for you sort of randomized output, and only if the output matches to your target, then you have a valid block. So this is like one way that a practical system is using randomized elements to solve problems with consensus. But hopefully I will have a more detailed talk about Bitcoin later on. So yeah, this table just summarizes the things that we discussed, with the addition of the quorum column here. And this is again very important thing to know, but also at the same time I feel it's difficult to convince yourself that it's correct, and even experienced people can have sometimes can be need to spend some time to convince themselves that this inequalities here are true. So yeah, a quorum, this is in our vocabulary the minimum number of processes needed to conclude an algorithm. And for the most part, and for your part in the labs, you can say that a quorum is the same as the majority of processes. So if you have let's say 9 processes, then everything from 5 and above is a majority. So we typically have 2 variables in the inequality: the n, which is denoting the number of processes in the system, and then the f, the maximum of processes that can fail, and the system can still continue to operate. So remember that we always know what n is before we start the system, or the initial condition of the system. We only always know how many processes there will be, and from this we can calculate f, meaning how many failures can we actually handle. So in the crash stop process abstraction, typically we need that n is at least 2f plus 1, And what this allows us to do, if we flip around the inequality, it will be that f must be less than half of n. So if we have this in predicate it's true, then there is at least one quorum of correct processes that can continue to operate. So if we would solve this f for 5 process, so that we have f must be less than 5 divided by 2. So 5 divided by 2 is 2.5. Kind of bad number maybe, but if we allow f to be 2 here, you cannot, whoever 2 process that you choose, there will always be 3 left. So you will always have a quorum of 3. So the n here is 2 times 2 plus 1. So 2, f is 2 plus 1 is 5. So totally we have 5 processes. And the quorum here is n divided by 2. So we round this up to 3. So it's not possible to have f equals 2 and there not be 3 correct processes. So this is somehow easy to see when you have only 5, and it is sometimes you can see this described that the yeah, here it says that there's at least one quorum of correct processes that can continue to operate. But sometimes you will see this as the in any quorum you will have an intersection of at least one correct process. So meaning that if A and D are the 40 process, and then the rest of them are okay. If we have a quorum of ADB and a quorum of BEC, then they will intersect on B, which is the correct process, and thus the algorithm will work correctly. And more difficult to reason about is in the case of arbitrary faults. So in this case, we have a majority must be larger, and here sometimes it's stated that 2 majority quorums may not have a correct process in their intersection. So again, if we calculate this thing out to say that okay, now we will have a quorum of 4, let's say. We can have B, C, E, F, and A, D, E, G, for example. Both of them are 4 processes, and F can be here too, because we have 3 times 2 plus 1, it will be 7, and we have exactly 7 here. And I don't know if I can, anyway, let's see if I can stop the presentation. We can draw a circle here. So let's see. Yeah, works somehow. So what I wanted to show you is that if we make this what's it called? We want to know if we have one quorum like this, guys. You see my point? And then we have another one. Let's make it. In the worst case, like this. So yeah, now you see we have one quorum B, C, E, F, and we have another one B, C, E, D, and yeah. So in the, I guess we could make this even more worse, but if B and C are failed, then in any of these quorums, they you have B and C in both, and you don't have a majority in any of them. So when you have a Byzantine fault tolerant, you require that your majority must be larger. So in this case, we need our majority to be, I guess, 5, and it will work. But the key insight to consider here is that a Byzantine process may pretend to be okay or be correct. So we cannot have the scenario here that we know who is correct because we have a failure detector. In the Byzantine environment, also they can pretend to be correct, and thus you can have false detections. Or yeah. So, any questions about that? Because now we are. Oh, okay. We have two more slides. Okay, let's go to that. Yeah. So the last thing in the book here, it's about measuring performance. So usually it's a good idea to yeah. Repeat last slide. I mean this slide. Okay, just a summary. Yeah. So the quick summary is that when we have a Byzantine fault environment, then we need to have um, this inequality to hold because our quorum must be larger than we had in the crash stop process abstraction, because here we say that our quorum can be any set of at least 3 processes is a sufficient quorum. But here we are saying that this must be it must be 2 majority quorums plus 1. So the quorum must be greater than 2 majority quorums. Yeah, so it should be. You can try to draw this out yourself as an exercise to reason about why it must be like that. But the key thing to keep in mind is that a Byzantine process can pretend to be correct, and it's also given here that the quorum, yeah, n over 3 or n over 2. Yeah, okay. Yeah, performance analyzing. There is not talking about analyzing your implementation, but analyzing the algorithms itself, meaning that on the exam you can be asked to reason about what is better between two algorithms, or define the pros and cons of two algorithms. So typically this is yeah, the way that you could do this, that you will first talk about the number of messages exchanged. So if there's a lot of messages, especially if it's a broadcast message that's being sent to all the processes, it will have a big impact on a real implementation. And also if there's many steps required, meaning that you send a message and you receive a message, you do some action, afterwards you send a different message and you wait for a response. You have different communication steps. So yeah, we can just see, because we have one sequence flow from way up here, that here, yeah, like I would say that we have two communication steps here from the processes. That there is one communication step from the leader to the replicas, and then also another step for them to do the acknowledgement. And the messages exchanged there, this is you only have two for the client, but you have sort of n plus n, like 2n, for all the processes that you would have. So we need to denote this thing that yeah, with n, like in the algorithms, usually it doesn't say how many processes there are. Just you must use like a n, for example, a variable. And we will see on Monday already, when we start with the broadcast algorithms, that sometimes you can have a broadcast to all the processes, and if all of these processes answer back to all of them again, you have kind of a square n squared messages. So this is sort of the metrics that you need to consider when you analyze the algorithm. But hopefully we will I will give an example of this on Monday. Yeah, and typically common guidelines for designing is to optimize for the common case, meaning that usually you don't have failures in your system, and you want the system to behave well in these scenarios, and also that you don't want the performance to degrade too much when you have failures. But we will see, especially when we go into consensus algorithms, that this is not the case, and oftentimes there is a trade-off of these things. Um, so, um, for example, if we see here the number 2, same performance independent of number of failures. I don't know. Sometimes I always have this word wrong. Anyway, so in the example that we just saw here, that so we can see here that the performance actually degrades a lot from the point of view of the client. That in the case that everything works, he gets his response back after one processing of the whatever storage operation. But when there is a failure, he only gets the response back after 2. And if you had more failures, that if the follower 1 crashed again after this, and then there would be another lead takeover, and another one, and another one, and another one. It can go on forever. So, and this algorithm clearly doesn't preserve this property, or the guideline here that has the same performance independent of failures. So yeah, you will hopefully we will see some interesting things regarding this. Okay, initially I had plans to do the gRPC today, but since we are already basically one lecture ahead of our plan, I will just do this on Monday, because yeah, we have some lab work to do, and you can spend 1 hour for this extra if you want. But if there is any questions, we can take this now. And I will answer best I can. Yeah, update the lecture plan. Yes, I will update the lecture plan for sure. I will write this down. And the course material, if you mean the slides, then I didn't share this yet, but I posted the YouTube videos or recordings of these lectures. But hopefully I will be able to share the slides as well. I just want to confirm that I can share with you with this copies of these algorithms. Yeah, I know that you mean this lecture plan. And also that yeah, if we can open all the lecture. Yeah, I'll try to open it 2 times. Yeah. Okay. So you see, it's to be posted. It will be, yeah, typically, yeah. Okay. I forgot to do it, but it's good that you reminded me. I will just take this up now. The current plan fast. Okay. Yeah, so I will post this on GitHub. Yeah, so we kind of moved our plan here that we just finished chapter 2, and instead we will do this on Monday. Yeah, regarding the book, yeah, it's probably not correct if I provide the PDF, but I posted the link to the book in this slide here somewhere. But yeah, it was kind of great. But I will post this link to the Discord. But if you go to this website, then you can download the book from the publisher's website. But you have to either be on campus or log into the VPN solution. So yeah, I will just post this to Discord afterwards. I can post it to the chat. Yeah. All right. So I will do that. I will update the lecture plan, and then we will go to gRPC on Monday, and also I think we will start on the reliable broadcast. Yes, and in March we will do. Yeah, in the March I will give you some research paper that you will need to read, and later on in April you should present this. So I put up 5 lecture days or times to do your presentation, but we will see how many students that will need to do this presentation part, because I know some of you did this last semester already, so it's only for those students that didn't do this part that need to do it again. Okay, any more questions before we stop? Okay, if not, then we will see each other again on Monday. Okay. Bye-bye.